speak here. But I think we better get started so that we don't get too late for dinner, because then we have to come back for another talk. All right, so for people that don't know Durham or haven't seen my talks before, I thought I'd just start by saying where we are, which is here in the northeast of England. And we have both warmish weather in the summer and cold weather in the winter. And we also have hot and cold Rydberg atoms. And we work on both. But here I'm only supposed to talk about ultra-cold Rydberg atoms. So we're part of this joint quantum center that involves Durham University and Newcastle. And we have a lot of activity in atomic AMO Physics. So a lot of BEC stuff. We have 3 different species of BEC, and there'll probably be a 4th fairly soon. We have a lot of activity on cold molecules, both here in the experiment with mixtures. So putting together rubidium cesium, ytterbium cesium, and we do magnetic slowing as well. And then we have a big Rydberg activity that involves a number of people. And we have a number of different species of Rydbergs now as well. We have rubidium, cesium, and strontium. And we're also doing some work on cold ions and cold electron beams based on ionization of cesium. And what I'm particularly interested in doing with Rydbergs is quantum optics. So the content of my talk will be mainly focused on light-matter interactions and the interesting properties that Rydberg have that modify that light-matter interaction. So the next slide sort of covers my activity. It's a bit sort of crowded, but it tries to get everything that I do on here onto one slide. So my main interest is in light-matter interactions in media with strong dipole-dipole interactions. So there's always dipoles when I send light through a medium, but usually those dipole-dipole interactions give a fairly negligible modification to the propagation of the light. You can create media, either dense media or media with Rydberg excitations where that's different, and the dipole-dipole interaction has a dramatic effect on how light propagates through that medium, and that's the kind of systems that I look at. And this kind of physics feeds into many different areas. It's quite interdisciplinary, and we see these topics cropping up in all sorts of different systems. So I think atomic physics provides us a very nice sort of model system in which to study this, but actually the physics branches out into solid-state physics and biophysics and all these other interesting topics. So as I mentioned at the beginning, we have experiments on both cold atoms and thermal atoms, and they give us different insights actually in these two systems. So our cold atom experiment is based on laser-cooled rubidium, and there we're very much interested in doing sort of single photon or doing photon-photon interactions that are mediated by the dipole-dipole interactions in the Rydberg manifold. And it's always nice when you have 2 laser pointers, because you can do an experiment, and you can also test how steady your hands are in front of an audience. So I can always test how nervous I am. But so if we look at these 2 laser pointers and I try to make them overlap, you see it's very, very difficult to align them. But basically you never see any photons scattering off other photons. So when I send 2 beams of light through one another, basically the interactions are negligible, and they don't really behave like bullets that collide and bounce off one another. But in these Rydberg media, and we'll hear more about this from Misha Lutkin's talk, you can really make photons essentially collide and bounce off one another, or at least modify them in interesting ways. And so those are the kind of experiments that we and other groups have been doing over the last sort of 5 years or so.
Excuse me.
Yeah.
You need to turn on the screens with this one.
Okay. Right.
Get by with one laser for a second.
So in addition to our cold atom experiments where we have a fairly controlled environment, we're also interested in doing experiments in thermal vapor systems. So the advantage here is that the setup is very simple and convenient. The disadvantage is it's much more difficult to gain the degree of control that you have in these cold atom systems. So the experiments are sort of simpler, but the theory is more difficult. And then in a sort of more extreme way, we're looking at dipole-dipole interactions for purely optical dipoles. So this is, for me, just changing length scales. So here I have a system with optical and microwave dipoles, and I'll talk a lot about this issue of different dipoles and different length scales. And the length scale of the dipole is basically set by the emission wavelength of the dipolar radiation. So in Rydberg systems, we do optical excitation, so we have optical dipoles, and then we have these microwave dipoles as well that have this much longer range. And it's this hierarchy of length scales that gives us the interesting physics in this system. Now in this system we only have optical dipoles, and we have to go to very high density to see interesting dipole-dipole effects. That we can do by heating these thermal vapors to high temperature, and we study them in very thin slab geometries, because then you still have you don't have too much absorption in the propagation direction, so you can still see some transmission and the light can still escape. Because the optical depth here is so large that you need to make the system at least say two-dimensional in order for some light to escape from the system and to study what's going on in there. So we study these thin slabs or nanocells where the thickness can go down to 30 nanometers. So this is a very interesting system. Actually from this we learn a lot of physics, I think, that then we can transfer to this about the dipole-dipole interaction. So as you'll see, what I present today will be basic dipole-dipole physics. And as far as I'm concerned, there are only dipoles. And the only difference between Rydberg and optical dipoles is one of the length scale. So we should really sort of bear that in mind, that there is only dipoles. But then when we branch out into all these different areas, then we get lots of different manifestations of the dipole-dipole interaction and dipole physics. Okay, so I have an acknowledgement slide. So these are all the people. I'm not going to go through them all, but there are various people, senior colleagues that work with me on each of the projects. But I'll just mention two people because they're here. So working on the Rydberg quantum optics experiment, and he's building a new setup, is Hannes Büscher. So this will be our next generation experiment that Hannes is building, and that's coming along quite nicely. And also here is Tom Ogden, who works on theory together with Robert Hopfliger, and they're working on more the theory in thermal systems, which is more demanding. All right, so those are all the people. So let's now talk about sort of what's our motivation a little bit. So I said at the beginning, actually part of my motivation is a fundamental physics one. I just like, if I can think of something that I can't answer, then I like to find the answer. So that's sufficient motivation for me to work on it. But generally people like to have something that might be useful. So in order to get funding, we have to think about what we can do with useful things. And the big theme here is either quantum information processing or now quantum simulation, depending on what audience and what country you're in. So let's talk about quantum simulators. And now, so now we have one. So one of the issues is from D-Wave you can go and buy these systems, and there's two ways of looking at that. Either that it's done, but most people would say it's not done and dusted because there's arguments about whether this is a real quantum processor or not, or just some kind of adiabatic quantum computer. But the fact is that somebody's built this and people buy it. So that's actually more of a motivation for us to make something. If we can make something that we can claim does some kind of calculation, then people will buy it, like Google or Lockheed or something like that. So that should be a motivation to all of us to continue with our activity to make something that does some kind of quantum simulation that could be useful to someone for some application. And until we've built it, we don't really know what it's going to be useful for. So the first thing is to build something that does something interesting. And this is the UK scenario. I thought I'd put this up because this is very recent. But actually, in the UK, the government's just announced a new investment into quantum technologies. And so this shows some famous physicists that you may or may not know. So this is Peter Knight. He's one of them. He used to be the president of the Institute of Physics. And this is Ian Walmsley, who works on photons and quantum simulation using photons. And this guy in the middle is our chancellor. So he's the money man. And they're all sitting there, and on the table is actually an ion chip assembly. So this thing goes into a vacuum chamber, and it's a piece of equipment from Alistair Sinclair that works at the National Physical Laboratory. So I like this picture because it shows, you know, people in government with serious money can actually sit around the table with a bunch of physicists, talk about physics, and have some real serious vacuum kit sitting there on the nice wooden table with all the wooden paneled walls. So I kind of enjoyed seeing that picture. So this thing is a serious business, quantum. If you can do quantum simulation, you can get serious money to do that. So that's one of the motivations. So I didn't put up a slide on atoms because I knew that Mark would be covering that. But basically, some of the challenges in this system, if you want to use some sort of qubits, are very sort of common to whatever technology that you use. You have sort of arrays of qubits that you then want to address, and then usually the addressing is done optically. Unless you're doing, say, some microwave or superconducting qubits. So this sort of shows the sort of challenges of getting all these different fibers in and addressing all these different ion qubits here. And in these systems, of course, in order to do all the processing, they have to move everything around and make one guy interact with another, which is kind of an advantage of the kind of technology that Mark talked about of the Rydberg system, where we can do a lot more processing without having to shuffle things around over reasonable distances. So that's the advantages and disadvantages of all these different systems. So the other completely different approach is to use photons as the qubits. So this idea has been around for some time, and what makes it very attractive is that the photons are very robust, and I can send them from A to B without them being destroyed or decohered. And the extreme example of this, you might claim, is that if you think of the blackbody radiation, it still preserves the polarization of however it was produced. So you could say that the decoherence time of photons is at least as long as the age of the universe. And so that's a very nice system. We can send these photons through room temperature systems like beam splitters, and they don't dephase or decohere. So photons are very nice. But the problem is, as I said, with my two, which I'm not, no, it's still there. I won't do the demonstration again. So the problem is with photons that it's very hard to make them interact. So the interactions are very weak. And there is no known way of making strongly interacting photons, except possibly by storing photons in cavities and things like this, but it becomes very demanding and very difficult. And it's still very demanding and difficult, so there's no way of doing gates. So we have these nice photons that have nice coherence, but there's no way of doing gates. So the only way of doing this is in some kind of probabilistic protocol where I use detection, and I use this Hongu-Mandel effect in order to make a measurement-based gate, and this is what's known as linear optics quantum computing. And so this is a large field that we often don't talk so much about in the atomic physics community because it doesn't involve any atoms, so it's just purely photons. Now here's a statement from Jeremy O'Brien quite recently. He says that the first 1,000-bit factorizing machine, so this is something that would go way beyond D-Wave because we don't think the D-Wave computer could factorize large numbers, so it's not a universal quantum computer in that sense. But this would be something that you would think you would take quite seriously. So if you can build a 1,000-bit factorizing machine, then people will take you seriously because you can start to factorize all these RSA encryption schemes. And so that would be something that would really break new ground. So that's something that, say, the quantum information or quantum computing community should be aiming for, is to build this. So it's ambitious, but that's what you've got to aim for to make something that's really interesting. And Jeremy O'Brien, who works in this linear optics quantum computing in Bristol in the UK, says this will be done with photons. And he's got a reasonable case that that may, in fact, be true. So let's look at how they would claim to do this, and this is the sort of schemes that they propose. And it's a fairly sort of simple thing that you have sources, you have, so the way everything works probabilistically, so that's the problem here. So the source is a parametric down conversion. So sometimes, the point is that if I create photon pairs, so if I detect a photon here, then I know I've got one there. But we don't know when that's going to happen. So what's the solution to that? It's to build loads and loads of them, and then for each of these ones that go click, for each of these channels that go click, I know I've got a photon, and then I route those into appropriate channels to do my processing. So I just basically multiply my system up until I've got enough semi-deterministic sources by this so this is called a multiplex source, and then I can make semi-deterministic or effectively deterministic single photon sources out of this multiplex source. And then I can do processing, and again the processing works by beam splitters and detectors. So again you have a high loss and you throw away things, but you can just make more and more channels, and you can scale up this. And roughly the estimate is that you need something like 10 billion of these channels to make this 1,000-bit factorizing machine. So you may say that's easy, or you may say that's going to be impossible, but certainly it's very demanding. But that's the way that they're proposing to do it in the linear optics community. So what do I say? I say if you add a bit of determinism, that's going to help. So either if we can add deterministic photon sources, which we know Rydbergs can do something useful there by storing single excitations and spitting them out, or if we can do deterministic photon processing, or both, then we can add something to this linear optics community, and we can basically massively enhance or take away this whole redundancy of these probabilistic protocols and make something that's reasonably scalable. And if we wanted to, we can build the whole thing on a chip using these waveguide architectures. We just need to get, say, channels here where we can put in our atoms and do the Rydberg excitation. So there's lots of challenges. We need atoms near surfaces. There's all these atom surface interactions, Rydberg surface interactions. But all these things are being studied currently in the Rydberg community, and we're gradually finding ways to deal with that. So I think this is a goal worth pursuing. So the difference between what Mark talked about, where all the processing is done in the atomic basis, is here that all the processing is done with photons in the optical basis, but we use the atoms in order to create the interactions or to create the deterministic photon sources. Okay, so that's the goal. And we have a scheme, so the details of this are maybe not so important for the lecture. I may come back to this in the last lecture, depending on how things go, but this is our scheme for all optical quantum processing using Rydbergs, and this should appear in, it's now accepted for PRL, so it should be appearing fairly soon. So if you want to read about that, kind of in this archive paper. And it's basically just a C0 gate for photons. So if I have a number of channels, and depending on whether I have photons in that channel or not, then I can change the phase shift. So if I have a photon in the control channel here, then I induce a phase shift on the target photon if it's also going down this channel here via a dipole-dipole interaction. So the principle is very simple. I use dipole-dipole interactions in order to make photon-photon interactions. But there's a lot of subtleties in this, and it's actually taken us many years. It still doesn't work perfectly, but it works a lot better than any other scheme that I know of currently. So that's currently our scheme and what we're working towards, and what Hannes is building the new chamber to demonstrate next year or so. All right, so that's my big overview of the kind of topics that we work on. And now I thought that because this is a school, I want to do some very basic physics, and I want to avoid too much overlap with Misha Lukin's talk, where he's going to talk about EIT and propagation and some of the similar topics to we work on. So I'm going to talk about some simple ideas and go back to the beginning of this dipole-dipole interaction. And as I said, it appears across this range of length scales between optical dipoles and Rydberg dipoles, and it's always the same thing. So I want to look at it in a very general way, and then we'll try and get more specific about that. So I think what I'll try and do is use the board a little bit, and we'll see how that works. So I'm going to try and write some stuff on here. So I don't know how well. Okay. That's not going to work. So if you can't see this, just put your hand up and tell me. So I'm going to give you my sort of 101 dipole physics, and really this is how I teach dipole physics, and I probably wouldn't teach dipole physics to undergraduates, but I really try to make it as simple as possible. So my general philosophy is always to do, yeah.
Is there a black or other color? It's not.
I'll try black. The pens are a little bit thin, actually, aren't they? Okay, so you see that? Yeah. So I have a field. Let's call it E0. Now this field could be lots of things. I've written up here. It could be a laser. It could be a microwave source. It could be another dipole, or it could be an image. So this source field could be lots of different things. It could come from anything. I don't mind at the moment. And then I have my atom that looks like a ball of charge, like this. And the fact that it's a ball of charge is important, but actually we're going to treat it as like an antennae, as an even simpler thing than a ball of charge. And then what happens is that this field induces a dipole in the atom. So when I have an atom or any system, it's neutral. There's no dipole moment. It just sits there. It's got no response. When I apply this field, then I get some kind of response. I'm going to actually write this as time dependent, so it's cos omega t. And then we do this trick of writing this, of just taking one of the complex parts of this. So I call this taking the positive frequency component. And this is important because you mustn't forget this half. Once you've done that, you've got to make sure that you put it in everywhere from then onwards. Alright, so now what we want to find is this thing alpha, which is the polarizability. So this is going to tell me how big my dipole is. And as I said, I'm going to do it classically. So what I'm going to say is that my dipole is just a little mass on a spring. So this is an electric charge minus E. It's got mass m. And it's got some binding coefficient that gives it a resonance frequency omega. And then this is the displacement z. And then it's a simple harmonic oscillator. So what I get is z plus gamma z naught plus omega naught squared z equals minus E over m E naught equals to minus I omega t. So this is the force here, normalized by z. And then this is the damping here. So we're going to come back to that quite a lot. What is this damping and how does it appear? So then I just substitute a trial solution, like say z equals z naught e to the minus I omega t, and then I get this solution. So everything I've done so far is classical. And then I do the equivalent of it. So normally our driving field frequency omega is not so far off our resonant frequency omega naught. And in quantum mechanics we always call that the rotating wave approximation. So we say that omega is close to omega naught. So I can write omega plus omega naught is about 2 omega naught. Now why do I do that? Well, because it basically modifies this term. So I can factorize this as an omega plus omega naught and an omega minus omega naught. And then I call delta the difference, the detuning, omega minus omega naught. And then the solution becomes E over m omega naught, and then 1 over 2 delta minus I. So I still haven't done anything quantum actually. I've just still got a classical oscillator that's got some damping. And then I have to do, now in order to map it into some quantum picture, I do my first bit of quantum. So I say it's a quantum oscillator. Please interrupt if you're not happy or... So what I can do is basically take this term here, so my quantum, so I got my length scale of a quantum oscillator, a harmonic oscillator length, A naught squared is h bar over m omega naught. And then I define an equivalent of the quantum dipole moment, where d naught equals minus e a naught. So that's just 1 divided. That's my effective dipole matrix element for my simple 2M oscillator. And then finally I get the result that's written on the board. And I can write that d naught equals minus ea naught is I d naught squared over h bar 1 over gamma over 2 minus I delta e naught. So that's the result I wrote up there on the board. Now you can do exactly the same derivation using, say, the optical block equations. And if you remember when you do the optical block equations, again you add this damping in a sort of ad hoc way. So we haven't said anything about what the damping is yet. And you don't really say, well, you say that it's basically the rate of spontaneous emission when you do it in the quantum treatment. So we'll come back to the damping in a minute. But once you've filled up the board, there's nowhere to go. Alright, so I'll leave the bottom and start. So now this expression is interesting because it gives us all these good bits of the atom-light interaction that we like. So the imaginary part of alpha is a Lorentzian resonance. The real part is a dispersive line shape. And then the phase, or the relative phase. So the phase goes from minus pi to 0. Sorry. And exactly on resonance, it's minus pi over 2. So again, this is classical oscillator physics, and we can easily demonstrate that by if I make something oscillate. I've drawn that wrong. I'm sorry, I've drawn this upside down. So it starts in phase and then it goes down to minus pi. So if I drive a resonator below resonance, then I go in phase, and if I drive it above resonance, then I go out of phase. And exactly on resonance, I'm pi out of 2, and I lag. My field lags behind the driving field. So if we think about what's going on now, we have this driving field, then it hits my atom. Then essentially a little bit of this field disappears. I end up with a less field than I started with. But now I end up with a new field, so what I've done is created this dipole here. And this dipole produces a new field. So this dipole is radiating. That's going to be what this damping term is all about. It's the radiation from the dipole. And this creates a new field, but this new field is slightly phase lag behind. So it's slightly behind like this. So if you imagine a medium now, we basically get loads of these dipoles. They're all doing the same thing. They're all producing waves that are slightly lagging behind, and this produces this wave that then travels more slowly. So this is the origin of refraction and dispersion and the propagation in my medium. Right, so I want to talk next about the damping term, gamma. I thought that just to make things a little bit more interactive, how would I get so we've got this damping term gamma. How would I express, so how would I derive a relationship between gamma and this dipole matrix over here? Any suggestions for how I do that? There could be more than one suggestion. Nobody wants to commit. I mean, do you know that? I wonder if many of you know the formula for gamma. So the question is, what is gamma? Does anyone know that? Even the dependent? No idea? Alright, so I guess we better no response. So let's derive it. Alright. So what we've got now, let's think about this. So a slightly different picture is we've got this field coming in, we've got this atom, we've got this new field that's created, the dipole. And essentially I can think of these, if I want to, I can think of these as photons. So this new field is a photon, and then we're going to get other photons coming out in other directions. So this radiating dipole is going to emit in various different directions. And if I assume that my dipole is basically like an up and down charge oscillation along the z-axis, then I get some kind of dipolar radiation pattern that's this familiar sort of antenna pattern. And the dipolar field for this, I'm not going to derive this, but it's on the board there. So just in the far field now, I'm going to talk about the far field radiation pattern. So my far field radiation pattern looks like this dipole. This is the induced dipole, 4 pi epsilon 0 k squared over r sine squared theta. Where theta is basically the angle relative to this z-axis now. So that's the dipole field line. So that tells me, if you like, the E dipole square tells me something about the distribution of the scattered photons. And now I want to derive the scattering rate. So the first thing I do is derive a scattering, a damping rate. So the first thing I derive is the power radiated by the dipole. I just integrate the intensity of the field, so I dipole, over all solid angle. So there's an r squared d solid angle thing, and I get some result for that. So I take this dipole field, I integrate over all some artificial volume here with radius r, and I get the power radiated by my dipole. And then I say, right, I know that this thing is a quantum dipole, so then I have to do my... This is the second time I introduced some quantum physics. So the first time was in setting this as a quantum harmonic oscillator. Now I'm going to introduce some other quantum physics, which is to say I've got a two-level system with a ground state and an excited state. And I'm going to say this radiating has to come from a decay of an excited state. So, and I know that this decay rate, because this is what we define it as, is gamma. So the rate at which photons are going to be emitted, which is what I'm interested in here, is going to be gamma times the probability to be in the excited state. So I've got some probability. And so that's my scattering rate, if you like, probability to be in the excited state times gamma. And then each time I get an energy h bar omega. So I can write that the power radiated is the probability to be in the excited state times gamma times h bar omega 0. That's the amount of energy that I get. So what I need to know now is just this. So I know that if they're exciting with some field E0, then I can, with a rate equation, I can get this probability to be in the excited state, which is a balance between the excitation rate, which is like a Rabi frequency, divided by the decay rate, which is this h bar gamma, and that thing comes in squared for the probability to be in the excited state. So what I do then is put all that together, so I've got this formula, I can do this integral, and I do it, and I get gammas on both sides, and then I rearrange things, and I get this formula, k E0 squared over 3 pi epsilon 0 epsilon h bar. So this is the scattering rate, or the spontaneous decay rate. Now, I think what's interesting about this is what we'll see in a moment, because I can write this in a different way, that this is an inverse length. So let's go here. So if I wanted to, I could write something like gamma equals d squared over 3 pi epsilon 0 h bar. And then this is an inverse length, so I'm going to call it, let's call this length r cubed, r0 cubed. So does that look like anything else that you know to do with Rydberg atoms or anything? So r0 is equal to h to the minus 1. Does this formula remind you of anything? heard lots of talks about it this morning. And what I write? I mean, it doesn't matter what I'm calling this big D0. This is dipole moment squared over 4 pi epsilon 0 r cubed. What's that? My interaction with the audience. Would it be insulting to say you're worse than Durham undergraduates? So yeah, I get a response from them. Anyway. Alright, so this looks like this is a dipole-dipole interaction. D squared over R cubed, dipole-dipole interaction. So what we see is that this scattering rate, and the dipole-dipole interaction have exactly the same form at a particular distance, big R equals a to the minus 1. And that's interesting and fundamental. What we'll see in a moment is that we can talk about whether photons are real or virtual, depending on whether we're in the near field or the far field of this dipole-dipole interaction. And in a sense, it becomes exactly when the time to exchange a photon, so if we talk about photon hopping, when this photon exchange rate is equal to the spontaneous emission rate, is exactly at this distance where gamma is equal to the dipole-dipole. So those two things match. So there's a crossover region between where we get radiative emission